Okay. Did we lose the leader? Okay, let me first of all ask a question, because we're trying to figure out how to actually make this effective for everybody. How many people that are here today could come tomorrow?
We are not decided. Still need a approval.
So approval, yeah. Okay. The reason I ask is that the background level here is it's a bit lower than what I had anticipated. So there's no sense in me going too fast, right? Otherwise, it's just like, okay, what was all that, right? So I need to go at a level that I can see that, okay, you kind of get it. Right? But that means that it's going to be very difficult to get through the material today. So another possibility is that, we could do, a fair chunk of the material today, but then tomorrow, on what's usually a DISC lab day, we could have a little bit of technical material and then talk about your research projects, and then we could talk about, maybe modeling for those people who are interested in, numerical modeling, talk about SIMPEG a bit, and, just have it so it's kind of at a bit more casual pace, but then you at least get something that's really valuable out. So currently, the Halliburton group, unclear whether you guys could actually make it. Don't want to put you on the spot, but if you could get permission, would you come?
Yeah.
Because there's certainly, I think the aspects there of the numerical modeling, and from your perspective, sounds like underdetermined inversion is kind of new to a lot of the stuff that you do. I mean, there's really a lot of overlaps here that might be useful. Okay. EM fundamentals. A motivation for this is, in fact, just this last example that we did. We put in a resistive layer up in here, and we're trying to find this sphere, and we're totally blinded by it. So we're completely shielded. But there's other things too. Sometimes you just have large areas, like this is 100 kilometers, or maybe you got rugged terrain or things that are hard to inject current in. So you need to do something different. So I just want to take you through some of the basics here for electromagnetics. I mean, how many people are familiar with Ampere's law and Faraday's law? This is stuff that. How many people are? Okay. Yeah. All right. Here's the basic experiment. We've got a transmitter and receiver that are being towed, let's say, in a bird. So you'll do this for some of your groundwater applications, potentially. That transmitter introduces, has got a primary field, okay, which looks looks something like this. So it's just a loop of wire, gives rise to a field, looks like that. This current is time varying, so you've got a time varying magnetic field on some sort of target that makes an electric field everywhere. So if there's a conductivity, then there's going to be current that's generated. And those currents generate secondary magnetic fields that could be measured at a receiver. The transmitter could have a waveform that's kind of like pulse. So usually we refer to that as a time domain system, or it could be a frequency domain system like this. And either are used. We're going to use equations in steady state. So what's called quasi-static. So we're just going to get rid of these displacement currents in Maxwell's equations and then solve for everything else. There's two important equations here. One is Faraday's law, which says that if I have the time-varying magnetic flux, I'm going to get an electric field. And that curl operator means it's kind of going by this right-hand rule that I think everybody's familiar with. And the other is Ampere's law, where we've got a current density J gives rise to a magnetic field. So again, there's a curl operator in there. So we just kind of look a little bit at both of those. If we've got a loop of wire, if we've got a straight line of wire, so just a wire current, then there's a magnetic flux that comes out, which is given by the right-hand rule. So there's a magnetic field that goes around like that, and that field drops off as 1 upon r. If we now take that wire and make it into a circular loop, then at each point in here we still have that right-hand rule going, but the magnetic field has an expression that looks like this and falls off as 1 over r cubed. So the magnetic field has that kind of direction, but falls off as 1 over r cubed. The strength of that magnetic field is importantly dependent upon what's called the moment. So the magnetic moment is the product of the area of the loop times the current. So Faraday's law is the following. So if we have a time-varying magnetic flux, that gives rise to an electric field. And the minus sign here is important because it helps tell us which way the currents are going. So the Earth likes to have magnetic fields that are constant. If you change things, it tries to make currents that oppose that change. So when we have a time-varying magnetic field, we get currents in here that are circular, and everything is connected through Ohm's law. J is equal to sigma. There is another app that you can play with. It's a 2-coil app. It's got a harmonic field or harmonic current that's going in. So we have a current that goes in like this, so it's sinusoidal. It gives rise to a time-varying magnetic field. And the app is going to be structured in such a way that there's basically an outer coil here, that's your transmitter loop, and an inner coil, which is your target. So your magnetic field is going to come down like this. What's important is something called the flux. So the magnetic flux is the integral over the area of B dot n hat. And we're going to represent all of that by an electric circuit in which this guy has got a resistance of R and inductance L. So it's from an engineering viewpoint, here's your circuit. You got a resistor, an inductor, and you got a current that's flowing through here. And the voltage that you obtain is equal to minus the time rate of change of flux. So that's basically the 2-coil app, and yeah, you can play with that and get some idea about what's going on. So here's what the app looks like. You've got various parameters that you can choose, and your target loop could be above that primary loop or below, and everything is going to be harmonic. For the two coil example, the primary field is going to be like a cosine. And you know, with everything, it's if the transmitter is a cosinal waveform, then anything that comes back is also something of the same frequency, but it could have a different amplitude, and it can also be phase shifted. So what we mean by that is, here's the red is the primary, and then the received current looks like this. So you can see it's got a different amplitude, and it's kind of phase shifted. There's differences in the peaks there. And that phase difference, because of the properties of a cosine, we can translate that into two parts. So we just break across the two parts. One of which acts as a sine, and the other acts as a cosine. And the part that is acting as a sinusoid, or sorry, as a cosine, is in the same kind of phase as the primary. So we call that the in phase. Sometimes we call it the real. So that gives us a part that works as a cosine. And then there's another part that works as a sine, and that's the out of phase part, or sometimes we call it the quadrature, sometimes we call it the imaginary. So that's the idea. So we're going to take a signal that we obtain, and we're going to break it up into two parts, one of which we're going to call in phase or real, and the other is going to be the out of phase, quadrature, or imaginary. So you're going to hear these terms, and if you talk to any person, let's suppose you've got somebody doing an EM survey for saline water out there, they might be using a frequency domain system, and they'll talk about the real part or the imaginary part, and that's where these terms come from. You have a signal that's coming back, and you're just simply going to break that up into two parts, one of which acts the same as what that driving current was, and the other which is out of phase. Okay, so that's actually one of those things that causes a lot of mystery to people like me. It's like, well, what are these guys talking about? You know, an imaginary data doesn't make any sense at all. But all it is just a way of decomposing things. And so keep this picture in mind, and you won't get confused. The phase lag that we have here, this psi, for the circuit model actually depends on the inductance, the self-inductance, and the resistance of the circuit. So it's given by that expression. And this quantity here, omega L upon R, is called the induction number. An important thing is the response function. So if I have my circuit model here and I change L and R and omega, if I make omega L upon R really small, so if I make it like a 10, then we'll call this the induction number. And you can see the dashed line here is the out of phase part. So the out of phase or the quadrature phase is actually bigger than the in phase part. So that's what happens when the induction number is low. When the induction number is 1, okay, then the two things are equal. And when the induction number is higher than 1, then the in phase part is larger than the quadrature phase. Okay, so this is an important diagram. So understanding what real and imaginary are in phase and out phase, and this response diagram are actually pretty important. So our two coil example, if we have some kind of a transient, suppose we've got a primary current that looks like this, our magnetic flux looks like this. The time variation, there's no change in time up here, no change in here, but right here we've got a step off, so it's like a delta function. And then our secondary currents in the time domain just simply decay. And they decay in a sort of exponential manner with a time constant tau, which depends upon L upon R. Okay, so now we've got these induced currents, and they generate a magnetic field through Ampere's law. So if we have any current here, then that gives us a magnetic field, and we can measure that at a receiver. Good. So that's the two laws. Then we have a receiver and the data. So we could measure a magnetic field, a B of T. We could measure any of its components. So we could use a flux gate magnetometer or something like that to do that. We could also use a coil and then measure a dB dt. And that coil is going to just measure a voltage. It depends upon its orientation. And yeah, coupling is an important part. Just to kind of reinforce that, this diagram is kind of a generic example of coupling. And remember we talked about the voltage that's induced in a coil depending upon the time rate of change of flux through it, right? So let's suppose this is a transmitter. So the magnetic field is like that. It's like that of a dipole. And if I put my target down here, here's my target loop, you can see that the flux is coming straight down through there. So there's good coupling here with the flux. Similarly, if I'm sitting out here and if I've oriented the loop this way, there's really good coupling. The magnetic field is coming perfect down that way. If I put up here, it really is terrible coupling, right? The magnetic fields are coming out. There's no magnetic field that's crossing that. So the flux through that is zero, so there's not going to be any voltage that's induced. So that's the idea of coupling. We need to have proper orientation of our receiver coil so that there's lots of flux that are going on. So this works for two things. It works for the transmitter and the target, but this could also be the currents in the target, and then this would be the final receiver. So the idea of coupling kind of works both ways. If you look in sort of original textbooks on electromagnetics, this is something that you'll see. You'll see a sort of a three-loop system, and what that represents is the following thing here. We've got a transmitter, gives rise to time-varying magnetic fields in our target, and that comes back up into here as receiver. So here we have three loops. So this loop 1 represents the transmitter. Loop 2 represents the target, and loop 3 represents the receiver. These coefficients in here are what are called coupling coefficients, and they just depend upon the relative geometries of the loop. So you can kind of see how they could have been generated in that previous diagram. And then the ratio of the secondary to the primary field is given by this expression here, where we just have these various coupling coefficients. And then we have this quantity here, which was our response function, and that's given by this guy, this guy here. So this three-loop system is actually, circuit model is actually pretty effective in trying to illustrate what is going on. So if we have think about a conductor in the Earth, and we've got a transmitter and receiver pair that are going over like this, then the signature of that is going to look something like this. And if alpha is equal to 1, then the real and the imaginary parts are going to be equal. If alpha is smaller, remember so now you're on this side, then the imaginary part is larger than the real. So if you looked at what your survey would look like, you'd have a quadrature part or out-of-phase part that's bigger than the real part. And it went the other way, then the real part is actually larger than the imaginary. In the time domain, you kind of have the same thing at different times. this is time on this axis, that's your value of response function. That's logarithmic, so you're just going to get straight lines here. If you did a profile over top, early time channels, you'd have the biggest response. Later time channels, it will decrease. So let's recap what we've learned. So we've got some basics of the EM induction, know something about response functions, mutual coupling, and we've seen data for time or frequency domain systems. And we've got a circuit model. The question is, okay, is that circuit model actually applicable to geologic targets? So we're going to look at a sphere in a resistive background. So we're going to have a transmitter receiver that's 20 meters above. So if you're flying something for your saltwater interface gear, that's a typical distance, height, 20 meters. And let's suppose you've got a conductor down here that's a couple of Siemens per meter. This is basically out in free space. If we go ahead and do the circuit model, we get something like this. If we numerically model this with a code, we end up with something that is basically the same. So the point about this slide is that the circuit model and numerical models kind of have a lot of the same features. So how do we do that? So this is something that has been developed at UBC. Lindsay, Heggie, and a number of other people have been involved in this. This is a two-dimensional electromagnetic modeling that's based on a cylindrical coordinate system. So I guess, I'm not sure you ever did cylindrical coordinate systems? Yeah, I thought so. Anyway, so this is a finite volume technique, works in frequency or time. It's built on SIMPE. So if, for those people who want to come tomorrow and want to see, okay, how would I do, 3D electromagnetic modeling, but with a 2D symmetry, how would I actually do that? Then we can tell you more about that. And there is an app at this point that will allow you to do that. So that's the SIL code that's being made available again through this open source initiative. And so what have we seen so far? That the circuit model is a good proxy. And the thing that we haven't accounted for yet is actually the need, so everything so far has just been done with a very resistive space. Okay. So what happens if you actually bury that target inside the Earth? Because now you're going to have to worry about how the energy propagates from the transmitter to the target and how the energy propagates back from the target to the transmitter. So that's important. Got to contend with it. So that's what we'll turn to next. How do the EM fields, fluxes behave in conductive background? So we've got to revisit Maxwell's equations. So here they were in the time domain. We put them together, and we have this equation now in as a second order equation when we combine them to get equation either in E or in H. So what have we got here? You see we've got three terms. So there's a Laplacian. And then this term here involves a first order derivative of H with respect to time. Okay, so that's our diffusion term. This is the guy that's important in quasi-static approximation. And then here's a wave propagation term. So this is the guy that we'll attack later this afternoon when we talk about GPR. For those people in seismic, this is, this is what you deal with. This guy here is just a bit of annoyance because he adds to an extra dissipation term. For most of what we do in EM, he doesn't play much of a role, and we end up in what we call a quasi-static formulation, and we just have that. So we end up with, in the frequency domain, take this, get Helmholtz's equation, looks like that, where this number k squared depends upon a real term in omega squared and then an imaginary term in omega. The quasi-static solution is when omega epsilon sigma is much less than 1. And in that case, the solution, if we have a plane wave, looks like this. It's got an attenuation term, e to the minus alpha z, and it's got a wave propagation term that looks like this. So that's sort of your phase. And the important thing here is something called the skin depth, which comes from this attenuation. And that is, the amplitude of the wave as it goes into the ground decays with respect to that parameter alpha. And there's a particular depth called delta, that's the skin depth, at which the amplitude has decayed to 1 over e. And the expression for that is given by here. In the time domain, if I put a pulse in, okay, then if I'm sitting, excuse me, at a particular, so let's suppose here's the surface of the Earth, somebody launches a pulse, and you're sitting here, the energy propagates into you, and there will be a time at which the maximum current or the maximum field is going to reach you. That time is given by this equation here. And also, if you looked at how what the magnetic field is as a function of time and where it has gone in the Earth after turnoff, at a particular time, this is what that pulse looks like inside the Earth. So unlike seismic, where you put a pulse in and it more or less travels as a pulse, EM doesn't do that. It diffuses through. So a sharp pulse in here just gradually dissipates as we go into depth. So again, there's another app. It's a plane wave app that allows you to put a plane wave in and see how it progresses as it goes into the Earth. So what's the effects of this background conductivity? So we had previously figured out what the exciting fields are from here, but now we propagate them into here and back here. So this is, I think, again, picture's worth 1,000 words. Here's our sphere. And now we're using this SIL code. So this is serious numerical computations. We've got a SIL code. There's a transmitter out here. And that's going to be basically a loop of wire. And it's going to have a time-varying magnetic field. And there's a frequency of 10 to the 4th hertz, so 10,000 hertz. If this is very resistive, then it's going to be just like the circuit model, but we can actually look to see what the currents are like. And this is the current density that you see on that sphere. So it's high current density right at the top and low on here, but you can see how it's illuminated that sphere. So that's great. We've got a transmitter up here. There's the currents on inside the Earth, and they're right on the sphere. Perfect. Let's change that. Let's increase it to 10 to the minus 2 Siemens per meter. And we're kind of yet okay. There's the currents that are still on the sphere. But let's change it now to 10 to the minus 1. So this now gets more conductive. And now you start to see what happens. A lot of the currents are up here. Those currents are up there because, well, they're being induced by this time-varying magnetic field. So we've got currents up here. There's still something getting down to the sphere. We can kind of see it, but it's not completely there. And then the next one, when we make this even 1 Siemens per meter, so it's still more resistive than this guy. I don't see it. It's completely showed. So that's the effect of the background resistivity. So if you look at that in the sequence, You should now start to kind of get a real good sense about, okay, I'm starting to get this, right? If I didn't have any background, then I've induced currents in my sphere, right? But the more I have a background that's coming in here, the greater the absorption is, and eventually I just don't see it. In the time domain, we're going to have virtually the same thing. Here's early time, t minus 5 seconds, and I'm going to step through the same sequence of conductors. So this is now 10 to the minus 2, so we're still seeing that. 10 to the minus 1, again, you can kind of see it up here. Lots of currents up there, and at 1 Siemens per meter, I'm moving. So frequency, time, doesn't matter. You still have that background conductivity that's kind of wiping out your ability to see it depth. And here's the summary. So what did we learn? We had what we had before, but we need to account for the energy losses due to the background. So let's look at some field examples. So the examples that I want to use in today's case histories are the following. So first of all, we've already looked at this one. This was DC resistivity. This one I think might be very interesting to you. It's Buch-Pernom, and it's a case of salination of water. So there's irrigation that's going on, and that's causing salt to get in. This one also might be very interesting. So this is an airborne EM data set to look at the near surface geology and try to understand how that's affecting the groundwater system. There's a Barrett Sea case histories where basically this is a marine EM survey and look to see what's happening there. Geothermal deposit, geothermal energy resource. This is Iceland, actually trying to find where the hot water is, where the resource is. Natural sources, we can use something called ZTEM. Ground penetrating radar, looking at rock glaciers. I guess rock glaciers aren't particularly germane to in Singapore, but the concept of using GPR for different kinds of problems, especially when you've got complicated stuff going on, is important. And then we're going to come back to Mount Isa and look at chargeability, the fact that conductivity changes with frequency. So the next thing I want to do is to look at inductive sources and play with some. So any questions while we do that? Yeah, so now what we want to do is to try to put the material that we've got into context of case history problems. So maybe if you take a picture that way, maybe it look like a full
Oh, it's actually full.
It is. Yes.
Yeah.
Yeah. So you have to look like it's. Yeah. Yeah. Speaking of success, we also need you guys before you go home today to fill out some kind of a review form. It'd be nice if you had something nice to say, but you didn't have anything nice to say. We need to capture it anyway. All right. Okay, so now we're going to look at inductive sources. So for those people who are interested in EM for water issues, this is particularly relevant. for the seismic group, there was a paper that just came out not too long ago. A guy named Daniele Colombo in Italy. Well, he works for actually Saudi Aramco. But the problem there with the seismic is that there's all of this complicated geology in Wadi Saba, especially, where they're trying to figure out, how to get the best out of their seismic data, and it's not working very well because of the near-surface structure. So you need to get near-surface structure, and in order to do that, what they're doing is flying airborne EM over that to try to get a near-surface velocity structure, which they're then using to help their static solution for the seismic, and ultimately getting out a much better seismic image. So all these things have a role to play in getting better information. Multiphysics. Did you show that with a flash? I think because if you go this way, it's going to be kind of. Did it work okay? That's right. Just take one with, because otherwise it's got the break. Do you know how to set a flash? Okay. Okay, let's see if I can do this. Looks like Okay. Okay, so what we're going to do is kind of go through the basic experiment again, transmitter receiver. Then we're going to look at the frequency domain, vertical electric magnetic dipole, and then we'll do this case history for groundwater. And then we'll do the time domain and do case history for near surface geology. Here's some important questions. Okay, this is what you're facing. Okay, what's the target? What am I really looking for? Right? Is that surface? Is that depth? Is it 1D, 2D, 3D? What? Transmitter. What's its location? Is it on the surface? Is it in the air? What's the waveform? Frequency? Time? What's the size? How big is it? What orientation? Exciting the target. What's the conductivity of the target? And the host, right? Remember, the host was real important. And what's the geometry of that target? So that's the coupling issue. The receiver of the data. What field should I measure? What instrument should I use? Coil, Flux gate. Where to collect the data? How many? How accurate? What's the depth of investigation? A lot of problems, right? There's a lot of stuff here, and so you can't expect that you can just sort of run up to somebody and say, oh, okay, what do I use, right? I mean, there's just a lot of stuff to be done, but a lot of these things kind of fall in the idea of the concept of the footprint of your transmitter, and they're really kind of questions of survey design. So it's a lot of stuff on the slide. Lots of questions, but let's just take it from the beginning. So again, the basic experiment, transmitter produces this primary magnetic field. We need to make sure we excite the target, we produce currents in here, and we measure them. So what's our transmitter? It's motivated by the fact that in some cases we've got large areas, let's say 100 kilometers. What's the size of Singapore? Yeah. Pardon me? 40 kilometers. 40 kilometers by what?
By 20.
40. What?
from north to south is 20 kilometers.
So 20 north and 40 this way. Yeah. So you could easily do all of Singapore with one airborne survey, right? And you might want to do that. I mean,
It's too urbanized. Is it?
yeah. So urban causes a problem, but
Why not? But then I'm wondering if that works only like such like.
yeah, but yeah, still 40 by 20. Actually, is it almost all urbanized? Yeah. Okay, I take it back. It was an idea. So here's a couple of systems. There's a frequency domain system. It's called Resolve. There's SkyTem domain system. That's a time domain system. This one's becoming very popular. Well, both of these are actually pretty popular for groundwater issues. For deep targets, remember I talked about the moment, which the moment, magnetic moment of the loop is? What?
AI.
Yeah, so it's the area of the loop times the current. So if you want to see deep, you need a big magnetic moment. This is one that's used. This is actually a couple of kilometers on the side. People actually do that kind of stuff. So our transmitter, just what I said, needs a big magnetic moment. If I run more loops of wire around here, then I can increase that magnetic moment. The important thing about the transmitter and exciting the target is that the fields from the transmitter, here's the magnetic field, falls off as 1 over r cubed. So any magnetic field that's coming down from the transmitter to here falls off as 1 over r cubed, and then maybe we had attenuation that was a problem. So you need to think those things. It also means that you want your transmitter to be as close as possible to your target. So if you're flying, helicopter is probably the best. Fixed wing aircraft have to be higher. Ground-based systems are really good, but they're cumbersome to use. And you're always concerned about coupling. For the receiver and the data, just went over this, you can measure a magnetic field directly or some kind of a voltage with a coil. Now let's look at the frequency domain system. There's something called the resolve system. So it's a series of loops. So there's a transmitter coil and a receiver coil. They operate at different frequencies, and you might have a number of them in a particular unit. How many people have used it? Anybody know what an EM31 is? Because for site characterization, if there's any kind of contaminants there or something like this, this is a mainstay in North America. So it just operates at one particular frequency, about 10 kilohertz, and you measure both an in phase and a quadrature phase part, and get a lot of information about what's there.
So 31 is the distance?
No, that's about 4 meters or 3 meters length. And it's just called EM31. GeoSci.xyz makes it.
Okay.
They just have to call it that.
It's going to be real strong.
Yeah.
31.
So remember our transmitter loop was like this, and then our receiver loop is like that. So there's a lot of coupling. There's a lot of primary magnetic field that's going through there. And so that gives rise to a big response. Because a frequency domain system is measuring all of this, what are called on-time data, and you've got this big response from the primary field, it can actually swamp out what you're looking for, because you're actually looking for something that's down here, and this stuff is swamping out. So what you do is you try to remove it, and sometimes they'll have another little coil here. It's called a bucking coil, and that has a magnetic field that goes reverse, and so that cancels out the primary field, and so then you're left much more with just the field from the Earth. So that's the issue there. And And then for things like this, or here, you just keep them in one unit so that you know exactly where everything is, and then that gives you some way of getting rid of that primary field. In the time domain, you have a current that goes up like this, and you have a response, and then your receiver, the receiver in this particular case is sitting here. So this loop, I think, is like 18 meters in diameter, and so that's your transmitter loop, and there's your receiver. Or you could have something that is you can actually have a transmitter that's on the ground, and then you could fly a magnetometer or something above it. That's what's done here. That's something called helisam. So you can have all these different combinations. You could have the transmitter up in the air. You could have the transmitter on the ground. You could fly a coil system up here. You could fly a magnetometer, and just lots of things. So that's kind of come down a little bit more to where to collect data and how many and how accurate. Again, seeing a few pictures helps a lot. So here's, when I say vertical magnetic dipole, or VMD, the reason for that is that it's, I kind of showed it before, but maybe I didn't emphasize it. So if you have a loop like this, okay, you've got a little loop, then you've got a magnetic field that looks like that. So it looks just the same as if you had a bar magnet. So it looks like a magnetic dipole. So a loop of wire kind of acts like a magnetic dipole. And what we're going to be interested in is the current density. So again, you can use the apps and kind of get an idea of what's happening. But we can answer a lot by current. We just want to look at where the currents are. Where are they? How strong are they? How do they change with the transmitter frequency? How do they depend on conductivity? What do the result fields look like? Okay, so we're going to do that. Here's the case. So this is a 3D volume, and there's a horizontal plane that we can look things at, and there's a vertical plane at which we can look at things. And our case here is this line here is going to be like the surface of the Earth. So we've got air up here. This is all still air. Here's our vertical magnetic dipole, 20 meters above the Earth's surface. This line is the surface of the Earth. Background resistivity is 100 ohm meters. Okay, so we're going to look to see what the response is of that. In cross-section, if we look at what the magnetic, or what the currents are, so here's our magnetic dipole, looks like this. So the magnetic fields are kind of coming around like that. And the currents in the Earth are high amplitude here and here. If we plotted in plan view, it would look like this. So the currents are flowing in the Earth. They're following the transmitter. So the transmitter currents are going like this. Okay. Currents in the Earth are also coplanar to that. And so what we're seeing here is that kind of circular path. We're going to look primarily at the cross section. So if we look at the magnetic field that's associated with that, in particular the vertical component of the field, you see that most of the magnetic field is actually down where the currents are, of course, right? So the currents are going like this in the Earth. So that's where the magnetic fields are. But there's still something up here, and that's where our receiver is going to be. So we're going to try to see if we can't see some effect. If we look at high frequencies, and remember I had this skin depth formula? So it looks like that. So we're only seeing 16 meters down. If we look at the currents, they look like this. So positive is coming out this way, negative is in that way. And the magnetic fields are actually kind of complicated. So you actually need to numerically model these things because things are actually, there's a lot of stuff that's going on. If I reduce the frequency, then I should be able to see deeper, right? And so you can kind of see that, and also notice that the magnetic field is actually simpler. So my takeaway message here is that if I look at 100 kilohertz versus 10 kilohertz, at 100 kilohertz, the currents are closer to the surface of the Earth. At 10 kilohertz, they're starting to expand outward, and the magnetic fields are going from something that's got a lot more structure and complexity to it, something that's simple. Okay, so that's a half space. What happens if I start to put in a layer? So now what I'm going to do is I'm going to take the same thing, it's 100 ohm meters background, and I'm going to put in a layer inside here that's going to have varying resistivities. So it's going to be, first of all, 1,000 ohm meters, so really resistive. And then it's going to be conductive, and then really quite conductive. And we're going to look at what the currents are like and also the magnetic fields. Maybe you should think about that just for a second before I actually show you. So we saw what what's going to happen in the case of a half space. If I now put in an intermediate layer that's really resistive, then what's going to happen? Remember when we did the DC resistivity experiment and the sphere? Like, it was a killer, right? Put in that thing that's resistive, and it's like, okay, we're finished. Do you think that's going to happen here?
No.
No. And why not?
Because it's induction field. Induction field can penetrate through the resistivity.
Right. Good. Go to the front of the class. Get your gold star. And for those people who are not working in EM. So remember we had this formula for skin depth, right? And skin depth is really large for really resistive materials. So what it said is just right. So let's take a look. So here's our current density for various types of conductive and resistive layers. If I have a half space, just 100 ohm meters, we see this. If I have 1,000 ohm meters, it's a little bit hard to see. It's much better on the screen. You can see that there's the currents are sort of up in here, and they're actually kind of almost sneaking into this into this bottom layer. If I have something that's conductive, now it's a bit more interesting. You can see there's stuff that's happening here, but there's this conductive layer. It's kind of like it's sucking the currents in. And so you can see how it's changed from here to here, how there's now some more stuff coming in. And if it's very conductive, interestingly enough, I don't see very much stuff at all. Here, it's like it's honing in on the conductive material down there. See, there's a couple of take-home messages here in that if you have a layered media, that the EM induction is going to really try to concentrate on what is conductive, and it's going to kind of focus in on that, and it's not going to be affected by the resistive layers. And the magnetic flux, turns out to be something like this. And remember, you're measuring things. So here's your transmitter, and here's what you're measuring. So here's the concentration magnetic flux, and it's the differences in these that are important. It's a bit hard to see on there, but it's called a sounding curve. So we're looking at the transmitter and receiver, but we're just changing the frequency. And then we're looking at what the vertical component of the magnetic field is like when we've got the just the half space, or when we just have the half space. So this is the real part, and that's the imaginary part. So remember, now we've always got this real and imaginary part for frequencies, and in this case, the imaginary part is higher at lower frequencies for lower induction. So that's what it looks like for the half space. Now put in a resistive layer, and really we haven't changed things very much. So the solid line is the same as we had back here, and the dashed line is what happens if you put in that resistive layer. So they're pretty similar, and the same for the real part. Okay, so we put in the resistor, didn't change it. But now look what happens when we put in that conductive layer. Now you can see the differences here in like with and without, as well as in here. And if you make it really conductive, then you've got something here. So these sounding curves now tell you, like, okay, I could really see the difference between, an Earth with that conducting layer compared to without. And if you imagine, well, row 2 here, 1 ohm meter, that's kind of like salt water. Okay? So you can see how different finding a layer, background with salt water is going to be compared to 100 ohm meters. So that's actually that's not such an unrealistic example at all. So if you've got saltwater intrusion coming in off the coast here, so you still have maybe the top X meters that's background, and then you've got the saltwater intrusion that's coming in that is going to be about perhaps an ohm meter, and that's going to be a huge response. So you can see that frequency domain system might be very, very good at detecting that. So now we come back to the shielding problem here. So when we have that resistor, just to remind you, for the DC resistivity, we've got that without the layer, and with the resistive layer, we were hooped, right? Now, if we come back to the EM problem, and again, you can solve this problem with that 2D cylindrical code. We look to see what the currents are like without any shielding layer. And so this is really interesting. So with just a uniform background, this is what the currents look like. So we got some in here, but we also see the sphere. Perfect. We put this resistive layer in. We get some in here, still see the sphere. There's basically no difference between this picture and this picture. So that's huge, and that's the basic take-home message for inductive source electromagnetics, is that you don't see resistors, and you're just basically transparent to Yeah, so if we looked at the at the sounding curves, we see that same thing. There's just hardly any difference. What happens if you have a conductor? So in the DC resistivity, everything got channeled through. We didn't see the sphere. In here, we unfortunately still have the same thing. So this is what we had without any conductor. Here we put the conductor in. We don't see any manifestation of the sphere at all. So the fact that you have a conductive layer in here means that, yeah, now you're still hooped. So DC resistivity got messed up because of a resistive layer. Inductive sources overcome that, but if you have a conductive layer, you still can't peer through. Okay, any Questions? Let's do a quick case history. So here's one called from Australia, Book Pernong. So the idea here was that there's a big project that was looking at salination. The challenge there is that you've got a region that has got a lot of irrigation that's going on. So you input water into the irrigation system, and then it can flow down into the river. It's called the Murray River here. And the question is, so this is irrigation up on top, and there's water that's coming down. The question is really, okay, is that saline water getting into this region in here where it's affecting all of the trees and the vegetation and getting into the river, or is it being held back? So we want to know that as over time to see, okay, how do we responsibly manage our water resources? The saline water is conductive, 3 to 5 Siemens per meter, and even if you mix it up with with the rock and stuff like that, it's still in the order of 1 ohmmeter. And fresh water is resistive, low conductivity, maybe like 100 ohm meters. So there's definitely a difference between the resistive and the conductive cases. The system that was flown was the resolve system. So it's got these multi-coils in here. In fact, it's got for horizontal coplanar. So the coils are like this, right? It's got all the way from 300 hertz to 130,000 hertz. So this is going to see the near surface. This is going to see deeper. And it's flying in lines that look like this. So here's, if you were in charge of this project, this is what you'd see. They'd show you some maps. Here's the low frequencies. So now you're seeing deep. And they provide for you the responses, the secondary over the primary. And this is now the in phase, or the real. So that's what you see. The contractor would provide you with that. And one of the things I'm hoping that you take away with is like, okay, now you see this in phase and quadrature, and you're not intimidated by it. You kind of got, oh, I kind of know what's going on. So here's the in phase, here's the quadrature phase. So it looks like this. So you can see that there's high values up in this region in both of them. And for the really high frequencies, which you're seeing more shallow, then you've got maps that look like this. Particular sounding curve at this location here looks like this. So the in phase is big compared to the quadrature phase. That means that your induction number is high or low? High. Thank you. So remember, you're on this part of the curve, right? So here's your response curve. And in phase is larger than the quadrature. So you're over here someplace. And that's what's happening here. So here's the in phase, here's the quadrature. So it's almost, stereotypical compared to what your response curve is. So now we're going to invert the data. You can invert data in 1D. You can invert it in 3D. This is a 1D inversion. Turns out to be good enough. And you make a conductivity model that is done by inverting each sounding. So each place that the transmitter is, you invert that in terms of a 1D. And then you do kind of a quasi 3D by requiring that things be smooth. And you end up with a conductivity map that looks like this. So this is at a depth of 8.6 meters, which actually looks a little bit below the depth of the river. And here you're getting the data nicely. So that's the conductivity model, and you see that you got all this yellow up in here, yellow to red. So that's high conductivities. The blue is low conductivities. And so now, by looking at this inverted model, we can start to make an assessment of what's going on, because the high conductivities, that's all the salt that's coming in from the irrigation. And look at the river here, right? So, well, below the river. So there's all this red stuff in here, which means we got salts coming in there. So that's all coming in here. And the way they refer to it is that, you know, the stream is gaining salt. It's gaining water from the outside. Whereas here, in these regions here, it's blue, and especially out here. So that's somehow telling you that there's fresh water that's going out. So the stream is losing water. So this is a pretty important impact, and it gives you a lot of information about what's going on at this particular time. You can also do it in time lapse by doing these surveys over multiple times. So here's the final synthesis. This is what that model looked like. You've got the Murray River down here. You've got all the irrigation, pasture that's happening up here. There's some perched water tables down here, and you've got stuff that's coming down. The question is, are the salts going into the river, or is there enough water in the river to kind of push the salts out? Simple question, but extremely important. And the conclusion is obtained through that. Okay, so that's the inductive source, frequency domain, big area, sounding curves, inverting, make some assessment about what's going on. Oh, we might actually even think we can do this. Okay, so now let's look at the same thing, but look at a different transmitter. So now we're going to look at the time domain transmitter. And we're still going to use a vertical magnetic dipole, and we're going to see how things go. So what we had before is that we had a frequency domain system, so that was just a harmonic. And we got a receiver that was also harmonic, and then we made it into an in-phase and quadrophase, right? For a time domain experiment, the good news about that is that if we turn the current off in the transmitter, then we have no primary field. So we don't have to worry about bucking coils or anything like that. We just don't have any time for primary field. And what we measure is actually the secondary response. That's why the time domain is such a nice thing to use. So we've got transmitter current, and that looks like this. And the receiver, if it's B, could be like this, or if it's dB/dt, looks like that. So again, we could use the app, and we've got the same scenario. We've got the same transmitter up here, but now it's having a time domain waveform. And if we looked at the currents, then the current densities look like this. Again, they're circular, so nothing changes. So most of the physics that you're thinking about is still conceptually holding. So we got currents going, into the board and out of the board, and they're sort of circular like that. And the magnetic fields are like that. So that's at a particular time. Yeah, so what I want to do is just to kind of show you like what happens in a time domain experiment. So we're gonna take this system, turn it off, and now the moment that we turn it off, we've got these currents that are induced in the earth, and then they're going to just disappear. So at 0.002 milliseconds, which is 2 microseconds, so small time, diffusion distance, kind of from one of those formulas that we had before, which is given by this, is only about 18 meters. So if we looked at the current densities, so they're going positive and negative, and they have that kind of a configuration. At 0.01 milliseconds, you can see how the current densities are flowing out. And at 0.035, they're up like that. And eventually, they kind of go like that. So if we looked at those currents are flowing in the Earth as a function of time after turn on. At very early, they're kind of compacted into here. A little bit later, they're like that. And for those people, Freddie, definitely. Remember Misak's paper about smoke rings, just talking about how the magnetic fields change as a function of time. They kind of tend to kind of follow those lines. And there's sort of famous paper just talking about how to think about things in terms of these smoke rings that are going on. So our important points here is that the currents flow in the same plane as the transmitter. The currents diffuse downwards and outwards. Each transmitter has got a footprint. The maximum resolution is controlled by the earliest time, right? So that's when stuff is really right near the transmitter, close to the surface. And the final depth of penetration is the latest time. Like, oh, okay, that's as far out as we go. Okay, so those are the main take-home points, I think, of this. If we look at a layered Earth, then we have now the same thing, and you can start to see that, okay, frequency, time, not so much different. In fact, I think that's an important point. If you look in textbooks, they often bifurcate. Like they'll do a lot of stuff on frequency, and then they'll do a lot of stuff on time, and it makes it seem like, oh, these are two really different things, but they're not. The only thing, like if you think about that app, the only thing is that, okay, I'm either changing my input current like this, or I'm really, and then stopping, pulling it back. So it's just all in how the currents are being turned on or off in the transmitter. So again, if we do this guy here, you can now imagine what's going to happen. Here's the half space. Here's our resistive layer. In the time domain, you can actually see things more easily. So look at this. So there's a resistive half space. Initially, we get currents that look like this. Then in the resistor, there's nothing, and then we're still seeing into the layer underneath. So it's like the EM waves kind of come in. They see the resistor, and they just sort of blast through, and they can still see part of the bond. If we put in the conductor, and you see everything is actually located in here. So you're not really so much sensitive to what's going on. So your resolution in the near surface is actually going to worsen because you have a conductor depth. So when you look at your saline water intrusion that's coming in here, you're going to see that you're most sensitive to actually the top of that saline water, and your resolution in the upper region might be decreased a bit. And then it's very conductive, it looks. And then your magnetic fields, follow that. And then again, you can see it's the same kind of thing for your sounding curves for UBDT. If it's resistive layer, they're basically the same as the half space. 10 ohm meters are like that. 1 ohm meter, it's hugely different. So this would be a very sensitive way of trying to find out what you've got. If you have a sphere or some target body that you're looking for, so now we've got a sphere. It's 1 ohm meter. It's the same that we had before. It's more of a 100 ohm meter background. And so now you're going to do this survey, time domain survey, over an area that has got this sphere embedded right in the middle. And at each of these places, you're going to make a sounding curve. Like so, each of these places, you're going to have a curve that looks like this as with time. And then you're going to plot it up. But we're going to plot it up so that we look at a particular time and then see what's there. And to make things a little bit easier, we're just going to look at this line here that goes directly over the sphere. And these are locations at which the data have been retrieved. So at the very earliest time, we get a really high response, 10 to the minus 5, but it's constant. As we go over over the sphere, we see the same thing as we do over here. And of course, that means early time, that's just like high frequencies, you're not penetrating it. Okay, so you're just seeing it. If we go down to a little bit later time, now we're starting to kind of see this guy. So we're diffusing down into the top, and you can see like the overall amplitude is decreased, but now you got a little bit of a bump. Okay. If I go down even more, 0.3 milliseconds, now I've really nailed this guy. So this is what it looks like in plan view, and you can see how that circular feature is manifesting itself, right? And my profile looks like that. So this is great. That might even be a bit of a sweet spot. If I go to later in time, now everything starts to decay away. Overall amplitudes are down, but I'm still seeing a little bit of an increase. And then at very late time, I don't see much anymore. So that's kind of the essence of things. You turn stuff off. Early time, you're just seeing very near the surface. Things diffuse through. There's probably a sweet spot there for time to actually see this guy, and then eventually it'll go away. So the receivers for a time domain experiment, same as we talked about before. There's a couple of different systems out there. There's something called a SkyTem system. That's the one that we're particularly looking at. And there's another one called VTEM. So this one's got the transmitter loop like this with a receiver here. This one's got a transmitter loop like that with the receiver loop in the center. And what you do is you measure different values at different times after turn on. So the input waveform could be something that looks like this, or it could be something that rises up and then is immediately turned off. You need to know what this input waveform is. That's huge. You got to know how it's ramping up, how it's turning off, when time t is equal to 0 is, what these time channels are, and then with that you can go ahead and convert things. So let's quickly do a case history. Yeah.
I want to know, in your opinion, what is the reason that for LWE, time domain technology's application is more limited compared with frequency domain technology?
That sounds like a really good question for tomorrow. There's a lot of stuff. That's a great question, and I think if we were able to do something with respect to understanding, or at least to understand how you could understand that problem, that might be very beneficial. So I want to do a case history that has to do with water. This is in Denmark. So in Denmark, so here's Denmark. There's a region in here called Kasted. The local geology looks something like this. There's a lot of incisions in here in which there's basically sort of till types of stuff, and then underneath there's sort of Paleocene clays. So the clays are very conductive, and what they're really interested in are these valleys in here which could have till and some meltwater sands and stuff like this. And they're trying to distinguish where these guys are compared to the stuff underneath. Okay? Because ultimately, what they want to do, I'll tell you the end story here, is that they want to know if they do something in here, like if they draw some water out here, what's the region that it's going to affect the water in other localities, right? So that's a tough problem, right? You need to understand what the hydrogeologic model is for that. And the question is, okay, how do I get my hydrogeologic model? It's got lots of terms and complexities. So here I'm going to show you how the time domain EM can contribute to this problem. The very first thing that, after having decided what the problem is, then we look at properties. So in this case, we've got different kind of units. We've got our buried valleys, okay, with clay underneath. We've got coarse sands and gravels that are infilling it. The clays are conductive, okay, and the water-bearing sands are much more resistant. So basically what we're doing is we're looking for regions of high conductivity. So remember, so we've got resistors here over a conductor, and that's like so ideal for our time domain inductive sources, right? Because we see conductors. So all of these things have got their own conductivity associated with it. We're going to use the SkyChem system. So it's got these guys is it's actually got two transmitters that are associated with one. One's called a high moment transmitter, so it's got a big moment, so it's putting in a lot of current, and the other has got a low moment. The waveforms are different, and the times at which they can compute data are different. This actually goes back to 12 microseconds. The high moment is 47. So two kind of a high moment and a low moment system all on one craft. The lines of data are given by this these blue lines in here. And we process the data. So basically at each location here, at each blue dot, there's a sounding curve. Okay, so a time domain sound. In fact, there's two of them, one for the low moment, one for the high moment. Those are each inverted in 1D, and then they're done with some kind of lateral constraint so that things are smooth. And then these guys here are then subsequently all inverted, stitched together, make a 3D model. So there's 9,500 soundings, 25 layers. So this is like a pixelized, and this is a depth slice of 5 meters above sea level. And we have resistivities in here. So the purples and the reds are very resistive. The blues are very low resistivity. So the blues are the clays. The reds, the yellows, the greens, that's much more indicative of, tills and cobble stuff and things that would be connected with where the water is. So we can use the conductivity inversion to estimate the depth to the clay. So in the end, that's like the main thing, right? We just want to know where the clay is at the bottom. So that's done to do this. This gives you a depth to the clay. And the red parts in here are the elevation, okay, of the clay above mean sea level, and the blues. So these are high elevation, so that's up like this. And this is at low elevation, so it's down like this. So you look at this and you say, well, there's all these valleys that are inside here that are indicative of till, and that's where the water is likely to be. So now you take that, okay, and you start to make a structural map, a 3D structural map of these different kinds of valleys and depths to the clay, right? And then you go ahead and now you've got a physical model of what everything looks like. So now you can populate that with hydrogeologic parameters. So we know something about the conductivities. So that'll help in determining, maybe what the material is in each of these valleys. So then you try to say, okay, this particular unit might, or part of that unit, might have, some hydrogeologic properties that are like this. And eventually, you build a three-dimensional hydrogeologic model. So the information from the conductivity was the depths to the clays, as well as some information inside that about what kind of material might be there. And then that has to be translated to hydrogeologic properties. But once you've got that, now you're in good shape. So now you've got a 3D hybrid geologic model. You can import that into some mod flow program. And then you can start to ask questions. Okay, so now you've actually got a serious 3D hydrogeologic model that you can do things with. So one of the things was, how connected are these guys? So you've got this big area in here. If I put a well in here and I start pumping stuff out, okay, where does the water come from? Is it coming from here? Is it coming from here? So if you put that into mod flow, then you can see, okay, so I'm pumping out here, I'm getting a lot of stuff here, but actually there's a little bit more things here. And notice how it's actually reaching way out into this valley out here. So I would expect when I'm pulling stuff out that I might actually be affecting the water that's happening here. So that's great, right? That's what you wanna do. You wanna have a hydrogeologic model that you could start to do things with and see, if I do something here, where is it affecting things up there? And then the same is with here. And actually, you notice if I pump here and here, it's not 100% connected, but it's getting pretty close. So it just now provides you a whole different scale of things that you could think about, because now you've got a representation there that you can do some experimenting, and you can make some critical assessment for the sustainability of your water. That's it. Good job. Okay, so before we break for lunch, Soggy's going to come up, and he's going to tell you, a little bit about the apps, and then with that we can then break for lunch, and then we'll come back and talk a little bit about that. Okay.
Hey guys. Okay. So I'm going to start from a little bit of big picture. So this is our website called GeoSci.xyz. So there are multiple pieces, and then we're doing this piece, DISC2017 now. And there's a GPG, which is for fourth-year graduate, like undergraduate students. And then there's EM, and Simpag. So Simpag is the open source package, which is an engine that we're running those programs, like that Doc showed. So it's a simulation and inversion package, open source. And we're mostly focusing on this EM part today. And so I want to introduce the apps. So if you go to em.geosci.xyz, so actually it's running. So if you have an internet, you can actually do it. And then there's a panel called apps. There are multiple things. There's fundamentals, static, frequency domain EM, time domain EM, and case histories. You can actually check it out, but not going to do that now. So we're going to go to apps. And there's multiple things. So there's EM apps and simulation notebooks. So how many of you guys are using Python? One. Okay. Have you guys tried the Jupyter notebooks? Have you heard about that? Okay. I'll introduce you today. So cool. So what we're going to do here, there's a link. It's called Azure notebooks. So Azure, it's a cloud computing. So there's some way, and there's some computers in somewhere, but we're connected that. And what we can do, so if you you need to make an account, but we already did it. But it's very simple. Like you need to just put your email address, and that'll give you. And what you can do, can you guys actually read here? So you just click. So if you click that link here, okay. So notebook.ozro.com, and then like it'll connect to this link, but like because you may not have an account, you need to type in your email address, and then that will give you this page, and then click this clone and run. So meaning like you're going to clone everything from the cloud and then run it. So what we've already done, but like I'm going to do the clone again. Cool. So then it'll move to this page. Okay. So this is the environment called Jupyter Notebook. So it's like an interactive coding environment. You can write the code or script, but you can actually run and plot it. Okay. So there are multiple applications. I might first show the DC app. Do you remember that sphere example that Doug showed, like a resistive sphere, conductive sphere, showing the charges? So what here, like you need to, there's a cells, okay? Can you see this green line? So if you click the cells, it'll activate the cells, and then if you press Shift Enter, and then that will run. So what it does now, it is actually installing everything in the cloud, okay, for on your account, and then so when like this bullets are solid, it means actually it's running. So, but like when it's empty, that's done. Okay, so we're good to go. And then I'm gonna run this cell. So it's running now. Star means running as well, and it's importing everything that we installed now. Okay. Yeah. So here's we have propose and what is the setup and what questions we have. So we're gonna so there are the parameters of apps, and then if I run this cell, that'll give this sort of. So here you have a survey. Remember, one asks like, which is the optimal survey for your problem? Is it dipole, dipole, pole, dipole, or pole, pole? So you can actually choose the survey, and then you can choose where the locations are, and then you can set the resistivity of the background and resistivity of your sphere, and then you can choose what you want to visualize. So I'm going to just make it small. Can you see that? Can you read? Okay. So let's say if I change, so row 1 is the background conductivity, and row 2 is the conductivity of the sphere. So let's make that as conductive, so 1 ohm meter. And then it shows the model. Right? So it's a sphere, conductive sphere. You got A electrodes and A and AB is like what we usually use, like current electrode. So let's say, okay, I want to see how the current looks like. So the current looks like that, right? So current flows, and then, yeah, you got this conductive sphere, right? And then current wants to suck in, and then just go back to B, right? And, okay, and then what happened for potential? So that looks like that, but it's kind of hard to see what's changing compared to the currents, but potential is what we're measuring. And then also you can see the charge buildup. But like most of the charge buildup at A and B location. So if you want to see the secondary charge buildup, you click this type, secondary. And then you can see minus charge buildup and plus charge buildup. Okay. So if I change our target to 1,000 ohm meter resistor, what happens? What happens on these charges? Martin? Disappear? Okay, so let's make it. Let's make your take your hypothesis. See that? So it's changed, right? It's flipped. Depending upon the conductivity contrast, charge buildup changes. Right? And also what we can do, okay, I want to see the secondary current, which is just changing due to the sphere.
And so that's perfect, okay? So, and here's how the app should be used. Okay, you you've got an ability to change a parameter. Okay? Before you press the go button, you change the parameter, and then think, okay, what's going to happen? Is that charge going to disappear? Wait a minute, that sphere is now more resistive than the background. So if the current is still going to flow in the same way, it's now going from basically a conductor to a resistor. That means I need to have a different, I'm going to have a positive charge there. And when it goes from that resistor to the conductor, then I'm going to have a negative charge. Just the same as if if I had reversed it so it's a conductive sphere, now going in, it goes, I've got resistive to conductor, that's the negative charge. Goes from the conductor to resistor, that's the positive. But the point here is that this is where you learn. You have something to work with. You ask yourself the question, what if? I'm going to change this. What am I expecting to happen? Before you do that, put your neck on the line and say, this is what I expect to have happen. And you press the button, and either two things happen. Either it comes out like you had predicted, in which case you now validate your understanding, like, okay, I know that. Or it doesn't, in which case, like, oh, what's wrong? I need to rethink this. I need to work through this. This is why these interactive apps are so powerful from the point of view of bridging that sort of technical information with your real understanding, and always being able to sketch out what's happening, why it's happening. It's huge. Great.
No problem. And then one thing that I want to comment was because somebody asked the sensitivity. I wasn't exactly sure who it was, but let's go back to 1000 meter. Okay. And then I want to see the sensitivity of this. We got one transmitter. Well, we got two electrodes and another two electrodes with potentials, right? And then if you want to see the sensitivity, and I might scale. Oh, sorry. Sorry. Okay. It's running. Yeah, so that looks like that. Yeah, it's got some plus and minus. It's very complicated. So let's make it a bit simpler. So I'm going to do a pole-pole. So I'm going to change the arrays to pole-pole. So you only got one a current electrodes and one potential electrodes, which is almost impossible. But let's assume that we got really far reference electrodes. And then, so what's going to happen? Say, if I move M electrodes to further, then its sensitivity changes, right? So let's move M to a bit more. Okay. Oh, sorry, that was M. Yeah, so it's changing. And then if I put it really far, yeah, so your sensitivity is much bigger. Much sensitive to the deeper part of the Earth. Then,
notice the change in sign that happens here. Right, so that means if you have a little piece of conductive material here on this side, you get a great big positive response. If you have a little piece of conductive material on this side, you get a big negative response. So it changes, that sensitivity changes sign. And you can also understand that by, oh, I've got a current that's going into here, so it's making a certain kind of charge, and so now I can understand. So you start to be able to put everything together so that you have a fundamental understanding. It's not just a picture. It's a picture that you understand and that provides some information.
Are you guys really hungry?
Yeah.
Do you want to stop here or one more app? One more app? Yeah. So then I'll choose frequency domain vertical magnetic dipole app. Okay. So basically, same thing happened. Install things and so see, this time is pretty fast, but because we've already installed everything, so it's just running things. So I import things, and then here we got frequency domain EM system, and we got 4 layers. Which this could be an air layer, but doesn't quite matter. You can like make that as a C layer or whatever you want. We got the transmitter and the receiver and a couple layers. Okay, so those are the parameters. We got some questions, and if you run that, so now you got okay, this type of picture, and then say. So let's think about the airborne system. They're usually like a 20 to 30 meter above. So you may want to adjust your like a height of your transmitter to say 20 meter. Okay. Yeah. So and then it's changed it, right? It's above the surface. Oh.
Yeah.
Wait a minute. Give me a sec. Okay, so now at 20 meter. Okay. And then, well, this is a magnetic field, but if you think about the frequency domain system, your primary is always at the same time with your secondary field. So like everything is at the transmitter location. But if you want to see what's changing as a secondary field, you can click this button, B secondary. You see, okay, it's very like a pretty low frequency. So if you want to change that to, let's say, 10 kilohertz, it's changing. And then you can change that frequency to 1,000 hertz or 100 hertz. So you can actually see how it changes in terms of frequency. You can change that to, can go up to pretty high frequency. Okay, and then, okay, what generates a magnetic field is a current, right? There's a circulating current. So, okay, how the currents looks like. Then I want to see J, but there's no, well, J only exists for Y direction. So you need to change that to direction. Direction means it's a vector, right? So we change to a non. And then still, we don't have a Z component. So we need to put Y component. And you can see the currents looks like. And then if you do the same thing for, so it's a pretty high frequency. Let's go down, go down, go down. Like that. So you can actually see what's changing. And then Doc showed, oh, if we put the conductive layer, what's going to happen? Say, yeah, put the conductive layer, that's changing. And you can change the height of these kind of things. Yeah, so yeah, that's you can change the scale, log scale, linear scale. So it's all available. Actually, if you got internet connection, and probably it may work for your phone as well. So you can definitely try. And then if there's any question, let me know while you're having lunch. So I'm going to be here. Yeah, let's have lunch. Thank you very much.
Okay, lunch. Thank you, Arthur, for lunch.
I sent you a PDF with the password, user ID and password for the internet. I don't know how many devices can be.
So anybody didn't sign in and
But
also
maybe if
you need to sign in. Also as the G registration and the didn't pay.
using that.
So anybody didn't pay and did not sign.
So
Yeah.
yeah, I mean, it also might be that people are happy to kind of share, like work,
Yeah, work
Yeah,
together.
like
Yeah.
the Halliburton team, right? Like Team Halliburton might want to just download one and then.
Food is outside. We get a sandwich each and coffee and tea. Yeah.
Yeah, we'll just play that part.
I see that you are pretty much sticking to.
Yeah, actually, I managed to. We'll finish this.
Are most of them gonna come tomorrow?
I don't know. Yeah, most of them I think were, and then Team Halliburton was uncertain.
Yeah, probably need their members.
Yeah. But, you know, given the kinds of things we're talking about, I think it's really helpful.
Yeah, especially for their tool sensitive.
Yeah, like